let's go ahead and get started. Today, we're going to review 6.3, and then we'll go over 6.4 as well, and then we're going to do a little bit of reviewing for the exam, just a small amount, not comprehensive at all, but just a little smattering. You have 6.3 due tonight. Please use 2 decimal places for the z-score and 4 decimal places for the areas, otherwise you will not get the right answer. Right? We talked about that before. The homework is going to assume you're using tables, which only have 2 decimals for z-score, so make sure you only use 2 decimals. Project Lab 5 is not due till the class after the exam. We went over a little bit last class. I anticipate none of you probably have worked on it yet, so you probably won't have questions until it's due. So I think we'll go over it a little bit more then. And then you have your exam on Thursday, covering chapters 3, 5, and 6. There's a review session tomorrow in 6:01 from 6:30 to 8. Are any of you guys coming to that?
Yeah.
Okay, oh cool. All right, good deal. We'll see you guys there. The exam has 2 parts. There's the basic calculator part, so you need a very, very, very basic dollar calculator. This calculator is way too smart for that. See all the buttons on there? So you see a really simple calculator. And then a graphing calculator. You all need a graphing calculator. If you don't have one, the library has some they can loan you. You just need a student ID. So make sure you have your student ID with you. Yeah.
But will they loan them since our class is so late?
Yeah, you can do. They have overnight checkouts.
Oh, they do? Okay.
Yeah, or you can just say, hey, I've got, and they should be able to do that. Okay, good. And actually, aren't they open till like 10 or something like that?
Yeah, you can drop it off.
Yeah, you can drop it off afterwards.
Oh,
Because
okay.
the exam starts at 7:30, and it ends at 9:30, and most of you guys won't need that much time. So, great. However, make sure you have to write down the formulas with numbers in them. You have to show your work. A lot of you guys are going to be upset and say, well, why'd you only give me half credit on this, and half credit on that, and half credit on this? It's because you didn't show your work. You just gave me an answer. I need to know not the formula, not the general formula, but the new formula with numbers in them. Right? Like 10 choose 5 times blank to the, 0.23 to the whatever times 0.77 to the whatever. Right? I need to see your work. When you're finding your standard deviation, you got to show me your work. You got to, show me your work. Also, make sure you bring your binders for extra credit, and make sure you put your quizzes all together in one section. And then these class notes that we're working on, put those in a separate section. That way I can flip through it really fast and it's all in order. And I don't have to worry about some people put them before the quizzes, before the chapter, or after the chapter, or in between the chapter, and it just gets really hard for me to keep track of all of it. And I need to go through them quickly, right, so that I can get through all of them before before people start being done with the exam. Okay. This is an important concept. Patrick, go ahead and read for us.
What is the range of values that the z-scores can be?
And?
What is the range of values that the area under the curve can be?
All right, so everybody with your neighbors, 30 seconds, try to figure out what those ranges are. What can z-scores be? What about your area under the curve? So z-scores, what can a z-score be? It can be anywhere from blank to blank. An area can be anywhere from blank to blank. What are those? Okay, so what's the smallest a z-score can be? Negative infinity. What's the largest a z-score can be? Positive infinity. What's the smallest an area under the curve can be? 0. What's the largest an area under the curve can be? 1, 100%. So it might help, if you're not sure about that, to look at a picture. Right? My z-scores are all the guys along here. Right? They're these guys. Those are all anywhere from negative infinity to positive infinity. The area So this is negative infinity to positive infinity. And the range of the values on the area that the area under the curve can be, that's this stuff here, right? This is my area under the curve. And remember, area is the same as area under the curve is the same as probability and percent. Someone else finish your sentence. Percent of population and relative frequency. Okay, good. So, Gina's going to ace this. All right, no worries. So the area of the curve is the same thing as the percent of population, right? This represents the whole population. It also represents the probability, and between two spots, the probability of being between those two spots, right? So all this, if you add up all of it, you better get what? 100%. 1. So, and you can never have 0 probability. So any small section can be anywhere from probability of 0 to probability of up to 100%. Zero to 1 or 0% to 100%. All right, so this is one of the things that we kind of did before, which I might give you an x value and ask you to find the area or the probability that x is greater than some number. So then what you do is you first convert your x value to a z-score. It's your first step. Then use normal CDF to find that area. And remember, I'm either going to give you one value and say find the area above it or below it, or I'll give you two values and say find the area between them. Right? If I give you two values, you got to find the z-score for this one and find the z-score for this one, and then use that normal CDF to find the area between them. And how do you find the? Well, we'll talk about that in a minute. Okay. Good. So let's take a look at problem number 1. Does anybody need another 30 seconds to finish this one up, or are you guys all good? All good? All right, so again, normal how do I know it's normal distributed? This is a normal distribution? It says normal. Good. Great. And normal, the two things I have to give you are the mean and the standard deviation, always. Right, so for normal distributions, it's mean and standard deviation. Binomial, it's N and P. But this one is normal, so it's mean and standard deviation. So you need this guy and that guy. Those are the two things you need. Now, less than 33. First thing you're going to do is find the z-score. Right? So what is our z-score? You take your x value, you subtract the mean, divide by the standard deviation. So this is going to be, I'll do it down here. So it's going to be 133 minus 105 over 20. And what did you guys get? 1.4. Great. Then you're going to draw a nice little picture. So again, this is how I want it. Give me the hill, give me the line along the bottom, and give me just a tiny notch only at the center, so I know where your mean is. 1.4, is that on the left or the right? Right? 1.4, I know I want above it or below it. Less than, yep, so below it. It's all this stuff over here. Good. And so then I'm going to do normal CDF. Last step. Of my left z-score, which is, negative 100. Sure, you can do that one. Comma 1.4, and you got 0.9192. That's this number in here.
want us to write it in the?
You don't have to. I like it if you do, but you don't have to. If you shaded it, then you might not have, it might, you know, people also do this sometimes, they'll do it like that, 0.9192, so it's kind of, you know, kind of like saying that's what goes inside of there. Yeah, I like that. More than 112. So again, find the z-score. So, Rosa, walk me through this. What am I doing?
You are going to do 112 minus 105,
Uh-huh.
and you're going to divide it by 7.
My standard deviation.
Oh yes, sorry, 20.
Uh-huh. Great. All right, so then you get 7 over 20. That's what you, yeah, that's probably you're thinking, 7 over 20? So,
Yes, sorry.
yeah.
So 0.35,
uh-huh.
then you're going to do the normal CDF.
So you do a little picture, right? And 0.35. Did you shade above or below it?
Above.
Above? So I'm to the right?
Mhm.
Okay, I'm sorry, and then you did what?
Normal CDF with the lower value of 0.35 and higher value of 99.
You did 99? Okay, great. And what did you get there?
0.3632.
Great, so this is 0.3632. Great. I don't know if I got to my person's last thing. I just realized something. Okay. Another thing I might give you is, say, given the area on the right, find the x value. So here, or given an area, I might give you the left area or the right area. If I'm giving you, if you're taking an area and you're converting it to a z value, the calculator needs to have the area on the left. You can find that though, either you're given the area on the left, which is easy, or if you're given the area on the right, you can find the area on the left because these two have to add up to 1 or 100%. Right, so this is 70%, this would have to be 30%. So find the area on the left, that's your first step. And maybe it's given to you, or maybe you need to find it. And then use the inverse norm of that area to find the z-score that splits that, that goes right here, to split this into that area on the left and that area on the right. Right? And then, last step is find the x value that goes with that z-score. Good, we did a couple of those last class. You have a couple of those in your homework, I think. The next thing is the quiz, uniform distribution. You are going to get 4 possibilities. The first one is, I just give you a distribution. It'll have like x's and probability of x's, and it's just a table. And I say, here's your distribution. Another one I might give you is binomial. Right, we talked about it a little bit. Another one I might give you is normal. The other one I might give you is uniform. Uniform, it's all equally likely. So that's why it's 0 probability of this, but from here to here it's all equally likely. And then again, it's 0 probability out here. It makes a rectangle. That's the thing that's nice about uniform. It's super, super straightforward. What do we know about areas under the curve? It's the same as what Gina said earlier. I'm sorry? Has to equal 1. Absolutely. So this area on the curve has to equal 1. And areas on the curve are really the same thing as probability and percent of population. Good. So those are all the same thing. So here, we know that this area has to equal 1. How do you find the area of a rectangle? Length times width. In this case, length times height. So we know the length times the height has to equal 1. then for this distribution, we can figure out what the height is. What's the height, what's the length? What's the length from 8? So what's the height have to be? 1 over 8. It's the reciprocal, because you multiply the length times the height, you have to get, has to be 1/8. You have to get 1. Okay, good. So now we know the height is 1/8. We can find the area of any little section. Here I want to find the probability between 4 and 6 minutes. So here's 4. Say this is 6. I need to find this area from here to here. It's a rectangle. What's the height of this rectangle? 1/8. We found that earlier. What's the length of this rectangle? From 4 to 6. If you're exactly at 4 minutes and you go to exactly 6 minutes, how long is that? 2 minutes. Make sense? So this is going to be 1/8 times 2, and you're going to get 2/8. You could also write this as 1/4, or 0.25, or 25%. I don't care. Any one of those will do. You can even leave it as 2/8, and I'd be okay with that, I think. That's not the point of this problem, this question. All right, do you guys need 30 seconds to consult with your neighbors on this one? No? Good to go? All right. Okay, so this is the other one we talked about. Central limit theorem. Remember, this is the mean of the means. So here, every single one of these numbers represents the mean of a sample of 30. I take a sample of 30, I find their mean. I take another sample of 30, I find their mean. I take another sample of 30, I find their mean. So I've taken all these samples, and these are all the means of each one of those samples. Central limit theorem says, even though these came from this uniform distribution, this bus waiting time, these means, these mean of means, they form a normal distribution. In other words, I expect them all to be around 10 minutes. They're all mostly centered around 10 minutes, and most of them are around 10 minutes, and fewer exist the further away you get from 10 minutes. Right? Most of them are right around 10, and then the further away you get, the less and less there are of them. So it makes this nice normal distribution. Super cool, really nifty. There are a couple of definitions for it. Haley, go ahead and read.
The sampling distribution of the sample mean is the distribution of all possible sample means with all samples having the same sample size and taking from the sample population.
Keep going.
Example, we have the numbers 1 through 40. If we were to take every sample of 30 of those and found their means, they would form a normal distribution.
Right, numbers 1 through 40. I take every possible sample of 30 that exists. That would make, and find the mean of each of those. Those means would form a really nice normal distribution. That's unrealistic for me to show you here, but I'll simplify it way down, and we'll just start with numbers 1 through 6, right? Uniform distribution 1 through 6, and take every possible sample of just 2 of them. So even reducing it even further. So n is only 2, so it's not going to be normal, but it'll start. You can see how it starts getting kind of normal-like. So every possible combination of picking 2, picking 2, picking 2, over and over again. So these are my possibilities. If I pick 2, I could get 1 and 2. I can pick 1 and 2. Their average is 1.5. 1 and 3, average of 2. 1 and 4. 1 and 5, average them. 1 and 6, average them. And then 2 and 3, average them. 2 and 4, average them. 2 and 5, average them. 2 and 6, average them. 3 and 4, average them. 4 and 5, 3 and 5, and 3 and 6, average those. And then left with 4 and 5, and 4 and 6, and then 5 and 6. So these are all the possible outcomes I could get if I took any 2 numbers and averaged them out of these 6. And you'll look and see they kind of, there's, here I'll show you the distribution of them. But like you can see, The 3.5s, there's the most of them. There's one here, there's one there, there's one there. So there's 3 of those. You guys see that? And there's only one of these. There's only one of those. But yeah, you'll see it sort of works out where it's starting to become kind of normal-ish, right? Just the beginnings of it. Just even with just a sample size of 2 and from a uniform distribution. All right, so now that you believe that this happens, this is how to find some of the basic things we need to make it work. Derek, go ahead and read for us.
If you average 30 points in a game, the game that borders on unusual is held to 50 points. If you randomly sample 25 games, the average of those 25 games will never be 50 points.
Right? So if I just pick one game, so this red distribution here, this red curve here, is the sample of of all of his games. And so if I just pick one of his games, I could get a 50-point game. It's possible. It's maybe a little bit unusual, but not super unusual. It's right on that borderline of unusual, right? But if I were to sample 25 of his games, there is no way I'm going to get I'm going to get an average of 50, right? I mean, it's just, because with a sample of 25, I might get some high games, but I'm also going to get some low games. You know what I mean? So it's just, they're going to kind of balance each other out, and I'm going to get something right in here. Just because that's the nature of things. If you take a large enough sample, the larger sample you get, the ones you pick that are out here, you're going to pick some that are out here. And they're going to kind of average out to be kind of in the middle. So this distribution for one game, you can get anywhere along here. But if I took a sample of 25 games and took all possible samples of 25 and averaged them, this would be the distribution curve. It's going to be like this in here. And you'll see, like, most of the time you're going to get right in this section in here. So which means that, remember, normal distributions, the 2 things we care about are the mean and the standard deviation. That's what determines everything about it. The mean says, where is it centered? And they'll both be centered at the same spot. But their standard deviation is different. This one has a much bigger standard deviation. It's wider, flatter. This one has a much smaller standard deviation. It's kind of all scrunched up in here. So how much smaller is it? It's this much smaller. It is sigma x bar, that's what we call this. In other words, the standard deviation of the sample means is equal to the regular standard deviation divided by square root of n. And that's, so anytime we're talking about a mean with a sample of a mean of a sample of size n, then instead of, whenever we do our calculations for the z-score, instead of using the regular standard deviation, we're going to use standard deviation divided by square root of n instead. Because it's going to be smaller. It's going to be like this instead of like this. Yeah? Okay.
What does the n mean again? What does that
N is the number of numbers we have. So n is nicely number of numbers, the sample size.
Okay.
There are a couple of, so yeah, this is just me reiterating what I just said a second ago. Brandon, with no. Go ahead, read.
Conclusion. Central limit theorem. Conclusion. 1. The distribution of sample x bar will, as the sample size increases, encode the normal distribution. Number 2. The mean of the sample used is the population. 3. The standard deviation of all sample used is sigma.
Yep. So the mean is just the regular mean. The standard deviation becomes small. It becomes the old standard deviation divided by square root of n. So, problem 3 on your quiz. Find mu x bar and find sigma x bar. If you didn't do it now on the next 15 seconds. Okay, what's mu x bar?
36?
Yep, it's the same as mu, so it's 36. What's sigma x bar? Yeah, it's sigma over square root of n, so it's 7 over square root of 42, and what did you guys get for that? Wait, what? 1.08. Good. All right, good? Okay, so we're going to move on. I want to talk a little bit more about these very quickly. First thing is, here's an example. So if you look at a regular normal distribution up top, that's just with n is 1, just a regular ordinary thing. But if I start taking samples of 10 and average them, another sample of 10 and average them, another sample of 10 and average them, so each one of these dots is sort of like an average of, they're all averages of 10s. You'll see it starts to scrunch up a little bit more. And if I take an n of 50, so sample size of 50 and average them, another sample of 50 and average them over and over again, it's going to make those means of a sample of 50 will make this much tighter distribution. You'll see how it kind of shrinks up, the standard deviation becomes really small, like 1/7 of the original one. And then here, uniform, like we talked about earlier, totally not normal. Do you guys see that? It's totally uniform in the top one. But once you start taking samples of size 10 and average them over and over again, sample of 10, sample of 10, sample of 10, it starts looking kind of normal, and sample size of 50 totally looks normal. It becomes a normal distribution. Even U-shaped, you can even go U-shaped, right, where it's the opposite of a normal distribution. If you take a sample size of 10, it starts looking kind of normal, and a sample size of 50 is normal. It's just kind of a neat thing. So here are some conditions for it. Gabe, go ahead.
If the original variable is not normal, a sample size of 30 or more is needed. And if the original variable is normally distributed, then any sample size of n will work.
Right, so if it's normal already, then it doesn't matter. It stays normal. So do you guys want just like another 5 minutes to finish up this problem here? Yes? No? Take 5 minutes. 5 minutes. If you finished it, then